microphone to Paul Messina. Paul Messina is currently the director for the exascale project or program from DOE in the US. He has a rich history in the US, where he has been at Caltech and at Argonne National Labs for many years. The last position at Argonne National Labs was actually Director of Science for the national supercomputing facilities there. And he's going to present an overview on the path for a usable exascale. Paul.
Thank you very much, Eric. Good afternoon. It's my pleasure to tell you about a project that was recently started in the United States and that I have the pleasure of leading. Now, one of the things that we do with the leadership computing facilities, the high-end computing facilities in the Department of Energy, is to meet periodically and organize workshops to look into requirements that applications will have for future machines. And so on the screen right now I have the covers of a few reports that documented a few years ago ideas for how exascale would help advance many different fields of science and engineering and national security. We have these meetings fairly frequently. In fact, last week I spent 2 days at a meeting to gather requirements from the nuclear physics community in the Department of Energy. So it's something that we do all the time. And as you might expect, we find that scientists can always identify advances that they can make if they just have more computing, where more computing might mean more I/O, more data, and as well as more power to do arithmetic fast. So the demand is there, no big surprise, but it's very broad. On the other hand, as you well know, and it's been remarked in many talks already at this conference, it isn't business as usual anymore in terms of getting the extra power from the computers that we use because of technology issues, physics basically. And so we can no longer count on the transistors, the circuits being faster based on the technologies that are used now. Instead, you see a flattening out and an increase in the use of energy. So, the way to symbolize this very easily, one of the implications for applications is that whereas when we went from gigaflops to teraflops, you got about as much speed up from parallelism as you did from the speed of the transistor, so to speak. Going to petascale, it was very different. Only 8 times the speed up due to the hardware, most of it due to vastly increased parallelism. And a rough estimate is that for exascale, it's going to come all from parallelism. So that means the applications have quite a challenge. There are many challenges, and in fact, one of the studies that was carried out by a committee was the top 10 challenges for exascale. And as you see them, it's what you would expect. Energy efficiency, interconnect technology. If you look down at number 8, algorithms for discovery, design, and decision, that had to do, among other things, with uncertainty quantification, because we clearly want to have some idea of the accuracy of our results. And that's always difficult, but when you're dealing with very complex phenomena and so much parallelism, one starts to wonder just how much can we trust the results. So there are a number of challenges. These are the top 10, and it's what you would expect. And so that means that to be able to satisfy the users who would like to have exascale, we have to perhaps do a little bit more work from generation to generation than we have had to in the past. And fortunately for us, this was recognized by the President of the United States. And last July, President Obama issued an executive order which established something called the National Strategic Computing Initiative. Its goal is to maximize the benefits of high-performance computing for U.S. economic competitiveness and scientific discovery. It's a broad program, a broad framework. As it happens with these things, it by itself did not have any money associated with it, but it does give the government agencies in the United States basically the responsibility of carrying out work related to the goals of this initiative. And so there are different agencies involved, in particular the Department of Energy, which is a part of the government that I've worked for as a contractor, is the lead agency within this initiative with the responsibility to execute a program. To put it in red, this is my way of focusing, to focus on advanced simulation through a capable exascale computing program emphasizing sustained performance on relevant applications. So I emphasize those things because the project that I will describe momentarily takes that to heart. The applications, sustained performance, a broad simulation type program capability is what we're aiming for. Now, the phrase capable exascale computing is something that has not been used that much in the past, and so, being a former mathematician, I thought we should define the terms, right? So the way we're defining it is, capable system is a supercomputer that can solve science problems, say, 50 times faster than today's 20 petaflop systems. So we're not measuring flops, but we're measuring performance of applications as a ratio. Power envelope of 20 to 30 megawatts, that's a lot, but still acceptable as opposed to, say, 100 or 200 megawatts. Resilient enough so that users will be willing to use it, so that perhaps it'll be 1 week in between times when a user would have to intervene in the application running because of a fault, either software or hardware. And I would say also a software stack that meets the needs of a broad spectrum of applications and workloads. So we want a capable system that meets those criteria and that's suitable for use by a broad set of scientific and engineering applications. By no means a limited purpose computer. So the approach that the Department of Energy has taken is to establish a project, the Exascale Computing Project, and it's run jointly by the Department of Energy Office of Science and the National Nuclear Security Administration, which is part of DOE. So from now on in this talk, I will typically just say DOE because DOE is really the umbrella for both the Office of Science, some other offices, and NSA. But it is a joint project, very much so. And the leadership team has staff from 6 of the labs. 3 are from the NSA side. There were more, Los Alamos and Sandia, and 3 from the Office of Science side of DOE, Argonne, Berkeley, and Oak Ridge. We have staff from 6 of the labs. Those are the labs primarily responsible for executing the program. But we expect that probably all 17 of the national laboratories will take part in the project in some form, applications development, for example. And one key aspect of the way that we organize the project is that we will be collaborating with the facilities that currently operate the leading systems at Livermore, Los Alamos, Argonne, Oak Ridge, Berkeley. And because they're the ones that will be operating the first exascale systems as well. So it's a partnership with them. And academia, as universities and industry, will also be partnering with us. So we're trying to take advantage of expertise and experience wherever we can get it so that we can end up with, hopefully, a very good result. And it's a 10-year project. So being a project means that we have milestones, we have phases. I'll describe some of those later. It is not, let's see what we can think up that's interesting in the next few years, write a few papers, and then decide what to do. It's very much focused research and development with milestones and time-critical activities. So the goals that we formulated to try to meet the needs of the NSCI, the role that DOE has, is, again, applications. Develop a broad set of modeling and simulation applications that meet the requirements of the mission needs for NNSA and DOE. Because unless we invest in those, it's unlikely that they will be able to be enhanced to address the problems they can't address now, while simultaneously running efficiently on the new hardware with new architectures. We have a schedule of 2023 to have a productive exascale capability, including hardware and software technologies. We want everything to be ready, the applications, software stack, and of course the hardware. And 2 or more facilities will get to systems, and although this slide doesn't say it explicitly, there's a goal of having 2 different architectures as well. We feel that that is important for a number of reasons. And to the extent that we can, we also hope to help HPC adoption in industry by trying to make sure that the architectures and the software that goes into our exascale systems can be very useful to industry, typically in much smaller configurations, but without having to dramatically change the software environment, for example, or the underlying hardware. So given that we have applications, software, hardware, and then the facilities as well, that's represented by exascale systems, one of the things that I like a lot about the project, but also poses a lot of challenges, is that we need to have co-design and integration of all these pieces. We don't want applications to go off on their own without paying attention to what the hardware will be like. And same thing for the software technology. And the hardware can't just be pursuing some interesting ideas. It needs to the extent possible, include features that the applications need to be more effective. And the exascale systems are the facilities, and so we want, again, the systems to be energy efficient, to have cooling technologies that the facilities can install reasonably, as well as software that the exascale systems facilities will need. So those 4 components of the project have to work together all the time. The applications that we will fund will have as a responsibility formulating carefully their requirements from the software stack and for the hardware design. And when, say, the software people propose a way to meet the requirement, then the applications team has to take the time to try to, in fact, use that solution, and if it doesn't work, iterate. That takes extra effort on both parts, or in many cases all 3 parts, but we think it's essential. It makes things more expensive in time and in money, of course, but we really want the facilities to end up with very usable systems. The people involved, of course, are the key to success as well, and this gives you a feel for the laboratory team that's leading the project. There are people from the 6 laboratories that I mentioned earlier. They all have extensive experience in all aspects of high-end computing, and so they will be working on this difficult job of co-design and integration among all parts of the project. So let me tell you a little bit about applications, a little bit more detail. So last summer, there was a solicitation for applications ideas. And so the Department of Energy asked all 17 of its labs, what would you do if you had exascale in terms of applications? And the National Science Foundation and National Institutes of Health also issued the same query to its communities. As a result, there were over 200 white papers submitted. And you can see the range of domains, those of you who can read, it's relatively small type in all these boxes, but the point is that there's a wide variety of application domains that were represented, from personalized medicine, precision medicine, to energy efficiency, cosmology, fundamental science, as well as very applied applications, manufacturing, for example. So clearly, we need to, if we're going to be successful, to develop an exascale capability that can meet the needs of that broad spectrum of applications. Now, we can't fund all of them, of course. That would be nice. But we do intend to fund a reasonable fraction of certainly the domains that are represented. Now, the funding, as I've already indicated to some extent, will come with strings. We will fund application development teams, and they will be required to identify, well, what problem, in some cases 2 problems, are they aiming at being able to solve as soon as there's hardware in place that's at the exascale with their software. So it isn't just we'll do better computational fluid dynamics. It has to be some identifiable real problem that somebody cares about. We want them to follow software engineering practices so that the software they develop can be maintained, typically open source, and others could take advantage of it besides the initial team that develops it. As I mentioned, there'll be tests to provide software and hardware requirements to the rest of the project. And unlike just research programs in this project, they'll have to execute milestones, and often jointly with the software activities, because as probably many of you know, the way that you do interdisciplinary research is by people working together. You can set milestones or joint goals, but unless you have the people working together, it's unlikely that you'll come up with a working solution. And so in this project, we will have milestones that are joint, but in particular, the way to ensure integration and co-design will often rely on having people from a software project that spend some of their time in the applications development team or vice versa. Within what we call the applications development focus area, we also will be establishing a small number of co-design centers. Now, these will be different from the ones that the Department of Energy instituted a few years ago, 4 or 5 years ago. Those were each focused on specific application domain, nuclear energy, combustion, materials in extreme environments. This will be more on methods, so for example, adaptive mesh refinement or particle and cell methods. Methods that are used by a number of applications, and try to develop better instantiations of those, both for the new kinds of applications, but also, of course, the hardware and software stack. And because there's so much leverage by good training of the people who develop the applications, there is a specific activity within this area of developer training. It could be short courses or even fairly extended courses, both on software engineering, but also on how to make good use of new software and new hardware architectures. Speaking of software, it plays a central role. So this cartoon is to indicate, we think of it as a bridge. You can sort of see in the middle there a photograph of a bridge. Sorry, it's not very good quality. I'm not much of an artist. But on the left, I put as proxies for applications the covers of some of those reports of exascale missions. So those are the applications, and they can provide requirements to the hardware. So that's the top blue arrow that goes to the right, as well as they're forced by the characteristics of the hardware. That's the red arrow going to the left, to have to change the way they implement their applications. The software, in general, though, will provide the bridge, and it'll provide solutions as well as some requirements, and certainly applications have to provide requirements for the software, same thing for the hardware. So software it's hard to say. Everything in this project will be challenging and essential, as I mentioned, has to be integrated, but the software has a particularly difficult task in meeting all those needs. And it has to be ready at the right time. Because, as you know, these high-end systems only have a lifetime of, say, 4 to 5 years. And if you take the first year or year and a half before the entire software stack is there, there'll be inefficiencies and wasted time for a large fraction of the useful life of the system. So we have put together a conceptual software stack. Now here we include near the top the applications in Codesign, but they're not at the very top because they will have requirements for correctness. I indicated that a little bit when I talked about uncertainty quantification, but also visualization, data analysis to understand the results. And so the applications need those to generate the ultimate information. Along the sides you see resilience going up and down the whole stack, because I see that as something that all parts of the software stack have to worry about. The algorithms, the programming models, the system software runtimes, they have to worry about resilience because there will be errors. On the right side are workflows, because more and more we find that some of the exascale applications will have different components. So, for example, experimental data flowing in real time to the exascale system for near real-time analysis. And so to orchestrate that movement of data and partitioning of what piece of the overall system does the computing and analysis, that requires workflows. And so we will be investing in workflow software. And then in the middle you see the more familiar things: programming models development, runtime systems for programming models, mathematical libraries, frameworks such as, say, PETSI, tools for debugging, measuring performance, for I/O, data management, I/O and file systems, and some software that will be aimed at some aspects of the coming architectures. I think you all know that memories will be more complicated, will have more hierarchies, and so there need to be software pieces for the applications to take advantage and manage which memory is used when. Now, some of the software will be developed and provided by the vendors of the systems that will ultimately be purchased. But some of it historically has been developed by universities and teams at the national laboratories, and I expect that will continue to be the case. And so we will be investing both in industry, universities, and national laboratory teams to put together this software stack. Much of the investment will be on things that already work now or expect to work in the future, but in every case they will need a lot of evolution because of the changing hardware and the applications that are changing their requirements as well. So a crude analogy that I think of is, well, I said the software is a bridge. Well, you keep the old bridge active and usable even as you're building a new bridge. And then the new bridge is new, but it isn't dramatically different from the old bridge. So what I'm saying is, I hope that there will be inventions of new programming models that will make programming easier and more adapted to the new architectures that are coming. But I am convinced that the current programming models, by and large, will continue to be useful. They need to be improved, and so it really requires a substantial investment, but they will meet a lot of the need, perhaps not all of it, but a substantial portion of it. So MPI, OpenMP, and related things will continue to be used. Perhaps you might think of them as the applications more and more not needing to be aware of them, but they will be lurking under there as support of some of the higher level abstractions. That's my opinion. In hardware, most of our funding will go to vendor industry. The initial step It's in fact just about started. Last week, I forget if it was Thursday or Friday, a request for proposal was issued. It's posted, and in a subsequent slide I'll show the URL, so that we want vendors to bid for contracts that last 3 years to come up with better node designs, better system designs for our applications. So we want to get a head start on improving the potential offerings of the vendors 3 or 4 years from now, or 3 years from now, when there will be a request for proposals for the first exascale systems. And there's also a design space evaluation effort, because we want to see, what the potential benefits are of the designs before they're built. So again, integration and co-design of everything I've talked about is key. And that's why I'm repeating this slide. I know it's the same slide, it's not a mistake. I just want to emphasize that. So, excuse me, I have fat fingers. Okay. The project is in 3 phases. The first 3 years, I've described much of what's going on. We will have applications development, software stack development, hardware design development, and that will lead to 2019. It will help formulate the request for proposal of the first exascale systems. That RFP will be issued not by this project, but rather by the facilities that will be housing those first systems, which are going to be Argonne, Livermore, and Oak Ridge, because that's the base plan for when those facilities need a new system. So starting in 2019, that will take place. And so the subsequent 4 years is when the systems that are under contract will be built. So that means the applications, the software people will know what the target architecture and vendor supplied software will be, and they can start to evolve their applications and their software stack so that it meets the needs of those systems. And the last 2 years is basically making sure everything is working well. So, we have detailed plans that are only skimmed in the time available. We've solicited proposals in the various areas. We'll be making awards this summer for software, co-design, and applications. Soon after, I think we'll be awarding contracts for the path forward, and there's the URL for that. So in this brief presentation, I wanted to emphasize that the goal of our project is to advance to exascale 4 things: a broad class of applications, the software ecosystem, hardware design, and also the facilities that will operate the initial systems, using a holistic approach with a strong focus on co-design and integration. And the work will be carried out by essentially the entire HPC community, industry, universities, and national laboratories. Thank you.